Hello bachcho, let's read the question. Examine the continuity and differentiability of the function fx, which is defined as mod of x plus mod of x minus 1 plus mod of x minus 2 for values of x from the set of real numbers. We also have to draw the graph of function fx. Solution शुरू करने से पहले let's note down the key concepts for this problem. So the first key concept is the definition for continuity for a function f at a point x equals a. So a function f is said to be continuous at x equals a if limit x tends to a of fx is equal to f of a. The second key concept is the definition for differentiability. So we have function f is said to be differentiable at a point say x equals a if the limit x tends to a fx minus f at a divided by x minus a exists and the value of the derivative of function f at a is equal to the value of the limit. So that is limit x tends to a fx minus fa divided by x minus a. So let's start with the solution by keeping these key concepts in our mind. Now the function we have been given is fx is equal to mod of x plus mod of x minus 1 plus mod of x minus 2 for values of x from the set of real numbers. Now we know that mod of x function is equal to x for values of x greater than or equal to 0 and minus x for values of x less than 0. Mod of x minus 1 is equal to mod of x minus 1 is equal to x minus 1 for values of x greater than or equal to 1 or 1 minus x for values of x less than 1. And lastly we have mod of x minus 2 equal to for values of x greater than or equal to 2, the function is x minus 2 and it is 2 minus x for values of x less than 2. Now let's try to write the function in piecewise form. So we have function fx equal to, so the function is equal to x plus x minus 1 plus x minus 2 for values of x greater than or equal to 2. So this turns out to, so let's just write it like this and then we will simplify further. So the next part we have x plus x minus 1 plus 2 minus x for values of x lying between 1 and 2. Next we have x plus 1 minus x plus 2 minus x for values of x lying between 0 and 1. And lastly we have minus x plus 1 minus x plus 2 minus x for values of x less than 0. So let's simplify. We have x plus x plus, so we have 3 times x minus 1 for x greater than or equal to 2. We have x plus 1 for values of x lying between 1 and 2. 3 minus x for x lying between 0 and 1. And lastly we have minus 3 times x minus 1 for x less than 0. Now what we have to do is examine the continuity and differentiability of the function fx. So first let's try to draw the graph of function fx. So here we have the coordinate axes So the definition of the function is f of x is equal to 3 times x minus 1 for x greater than or equal to 2, x plus 1 for x lying between 1 and 2, 3 minus x for x lying between 0 and 1, and minus 3 times x minus 1 when x is less than 0. So now let's draw the graph. For the interval 0 to 1, the function we have 3 minus x. So at x equal to 0, the functional value is 3. At x equals 1, the functional value is 2. And since it's a straight line, we can join these 2 points to get the graph in the interval 0 to 1. Next, at x equals 2, the functional value is 3. So again here we have 3. And let's join and get the graph in the interval 1 to 2. Then at 3, the functional value is 6. So here we have somewhere around 0.3, 6. And the graph in the interval 2 to 3 looks like this. And for x greater than or equal to 2, this graph continues, right? So this goes on. Next, for in the negative side, for x less than 0, the function is minus 3 times x minus 1. So let's compute the functional value at x equals minus 1. So there we have 6 again. So the point is somewhere around here. So let's join these 2 points to get the graph. So we have, and this graph continues towards the negative side. So here you can see in the graph, you can see that we have sharp points at x equals 0, x equals 1, and x equals 2. So by graph, you can see that we have 3 sharp points, and at sharp points, the function is not differentiable. So the potential non-differentiability points are x equals 0, 1, and 2. But let's check theoretically, so whether our claim is correct. And also you can see that the graph, from graph we can tell that the function f is continuous throughout the domain. So now let's check continuity of function f. At breakpoints, so the first breakpoint let's consider for x equals 2. So here we have limit x tends to 2 minus of fx. So to the left of 2, the function defined as x plus 1. So we have x tends to 2 minus of x plus 1, which is equal to 3. Then to the right of 2, we have function defined as 3 times x minus 1. So we have limit x tends to 2 plus 3 times x minus 1, which again gives us value 3. And also f of 2 is equal to 3. Therefore, f is continuous at x equals 2. Now, for x equals 1, let's check. So we have limit x tends to 1 minus of fx. To the left of 1, the function defined is 3 minus x. So we have limit x tends to 1 minus of 3 minus x, which gives limiting value 2. To the right of 1, we have limit x tends to 1 plus. To the right of 1, the function defined is x plus 1, which again gives the limiting value 2. And we also have f of 1 equal to 2. So therefore, f is continuous at x equals 2. Lastly, for x equals 0, we have limit x tends to 0 minus of fx. So to the left of 0, the function defined is minus 3 times x minus 1. So we have limit x tends to 0 minus 3 times x minus 1, which gives the value 3. So for to the right of 0, so x tends to 0 plus, the function is 3 minus x. So here we have limit x tends to 0 plus 3 minus x, which again gives the limiting value 3. And so here also f of 0 is actually equal to 3. So therefore f is continuous at x equals 0. Now let's check differentiability by definition. For x equals 2, we have to check whether the limit exists. So limit x tends to 2 minus of fx minus f of 2 divided by x minus 2, which is equal to, so to the left of 2 the function defined is x plus 1. So we have limit x tends to 2 minus of x plus 1 minus f of 2, that is 3 divided by x minus 2. So this gives limiting value 1. Next we have limit x tends to 2 plus function fx minus f of 2 divided by x minus 2. To the right of 2 we have the function 3 times x minus 1. So we have limit x tends to 2 plus 3 times x minus 1 minus 3 divided by x minus 2. So this gives us 3. So therefore, since the limits are unequal, so we have unequal limits. Therefore, f is not differentiable at x equals 2. Now, for x equals 1, let's check the limits. So we have limit 1 minus fx minus f of 1 divided by x minus 1, which is equal to limit x tends to 1 minus of. So here we have the definition of the function. To the left of 1 is 3 minus x. So we have 3 minus x minus the functional value at 1 is 2. So here we have 2 divided by x minus 1. So here the limiting value is minus 1. Next, limit x tends to 1 plus fx minus f of 1 divided by x minus 1, which is equal to limit x tends to 1 plus, to the right of 1 the function defined is x plus 1 minus 2 divided by x minus 1. The limiting value is 1. Again we get unequal limits. Therefore f is not differentiable at x equals 1. Lastly, for x equals 0, we have limit x tends to 0 minus of fx minus f of 0 divided by x minus 0. Now, to the left of 0, the function defined is minus 3 times x minus 1. So we have limit x tends to 0 minus of minus 3 times x minus 1 minus the functional value, that is 3 divided by x. So now this evaluates to so we have minus 3x plus 3 minus 3 cancel, and so the limiting value is minus 3. And to the right of 0 we have limit x tends to 0 plus fx minus f of 0 divided by x minus 0, which is equal to limit x tends to 0 plus of, to the right of 0 the function is 3 minus x. So we have 3 minus x minus 3 divided by x, which is equal to minus 1. Again we get unequal limits, and therefore f is not differentiable at x equals 0. So therefore we can conclude that the function fx is continuous for every x in the set of real numbers, but fx is differentiable for all real values of x except at x equals 0, 1 and 2. So this is our final answer. I hope you understood it well. Best of luck and thank you.